All right, so we're going to start with the lesson. I'm actually going to start with the top portion of number 1 to explain all the little small details in this square on the top. And again, I've copied each of these on every single page. On the exam, whether it was in the classroom or we do this remotely, on the exam, you will also get this exact same square or box with the exact same information. I just copy and paste it. The only difference is that if we were in the classroom, it wouldn't be a color copy. It's really nice that now you can see the Roy G. Biv colors, which will help. But I'm going to go over how to know this, even if it's black and white, what you can do to remember where everything goes. All right, so I'm going to ink some information to start with so we know what everything represents. Let's see, inking. Okay. The E here represents energy. I'm going to write that down in there. Just take a few notes. Your H, let's see. Maybe I'll highlight it here. Okay. Your H represents something called Planck's constant. It is a constant. It's already been established by Max Planck, and it's nothing that you need to memorize. It will always be given to you. Again, regardless of where we're testing, in the school or remotely, it'll be given to you. It is 6.6.
We can't hear you. Your mic is messed up.
All right, so Planck's constant is the 6.6 times 6.626 times 10 to the negative 34. And the J represents joule, which is a unit of measurement and for energy. And S represents second, or seconds. And then we have a symbol called nu. It looks like a little V. And this would be something from physics class from last year. However, the little new sign is down here. So if you don't remember what that is, I'm gonna highlight information here for you. Let's use the green. Frequency. And then I'll highlight a different color, blue. Wavelength is that symbol right there. Okay, so just so we know what they are, but they are always given to you. So we have, let me highlight this. Oh, I just erased it, sorry. There we go. All right, so frequency times our Planck's constant, we can solve for energy. Well, what do you mean by energy, Mrs. Selkson? So this is going to bring us back to the lesson that we talked about last week. And let me get back to the inking. So if we're talking about our atom, we're looking at each of these energy levels. So here I'm depicting 3 energy levels. Remember that because it's circular, when we write it out, we made them into lines. So we've only shown a segment of this. So we would have shown a segment such as this. 1, 2, 3. So my energy level 1, 2, and 3. Energy levels are lowercase n. It's just another way of mentioning energy level. So here we have 3 energy levels. We learned that as our electrons move up on an energy level, it's absorbing the energy, but it's not until they jump from high energy level to back down to ground state or back down to a lower energy level, that's when they emit energy. That energy can actually be visible light, which we'll see in this chart here. I'm going to go over it, kind of see my cursor going over it. It can be visible light, and visible light is right here in that line. That's the whole, it's a blown up version. So it goes from about 350 to about 800 nanometers. That's visible light. Anything below that, you'll notice, is below the visible 350. If it's lower in nanometers, it's going to be ultraviolet, X-rays, or gamma rays. If it's above, we have infrared and radio waves present. So again, we're going to go back and show this image. So if we are going down, let's say 3 to 1, excuse me. If I'm going 3 to 1, I'm going to be giving off some sort of energy. I don't know what that is. I can predict it. If I'm comparing two different jumps, I can predict it without any calculations, but that's theorizing it. It's not until we calculate it that we can actually determine exactly what type of energy. Is it visible or is it not visible? But we can calculate that. And that's what today's lesson is all about, is what's the calculation. So we're going to show you the theoretical and then show you it calculating it wise. So back to my equations on the left, if we're solving for energy, and I don't even know what kind of leaps they're taking, I don't know the energy levels, but I do know frequency, how frequent those wavelengths are, I can actually calculate your amount of energy. And from the calculation, I can determine what type of energy is being emitted. If, let's say, I know that. Let's say I don't know frequency. I only know the information that Mrs. Elkson wrote up here. I only know, for example, that the electron went from energy level 3 back down to energy level 1, and it emitted energy. You can do a calculation by using, oh no. Let's do this one. You can use this right here, this equation. This equation is using another constant. That constant is right here. Okay. So the RH constant is 2.180 times 10 to the negative 18th joule, which is a unit of measurement in energy. You would plug that value in, and part of the equation says to make it negative. Then it tells you to use the high. So the highest N would be the energy level, which in this example, I gave you 3. The lowest energy level for this math equation would be 1, because that's the example I just happened to give you on the top right corner. So you could actually solve for the amount of energy and then refer back to this electromagnetic spectrum to determine what type of energy is being emitted. So let's go on further for the equations, just so we're clear. This is something that we've repeated from physics class. So the speed of light is the symbol of a lowercase c, and it's equal to frequency times wavelength. The exact speed of light, we tend to be a little bit more precise in chemistry. You use 2.998. However, many of you just have rounded it before, and I have no problem. In fact, I probably just will use, I'm sorry, meters per second. I'll just use 3.0 times 10 to the 8 meters per second, because I believe that's the one that you guys are comfortable and have used in the past year. An equation that you need to know to convert, this is convert to meters to nanometers, is this. And we're going to use proportions to convert, and I will show you the math involved to this. All right, let's take a look at this image so we understand the image before we go on any further with the math. The image over here to the right, we discussed the electromagnetic spectrum, but I want you to notice the top portion, so follow my cursor. The wavelength increases as we go to the right. That means the wavelength increases as there's lower energy. So the reds, and if I'm looking at visible light, the red and orange would have longer wavelengths, while our indigo and violet have slightly shorter wavelengths. And the energy is increasing. So frequency is increasing, wavelength is decreasing, and we have the examples of what you would see to the left. This again will be given to you on the test, this exact image. So utilize the fact that I've given you this information. Your first question is not mathematical, so I want to go over it together with you. It is actually a theoretical question. It's saying, let's say that you have an electron A, underline information, transitions from an excited state of 4 to ground state 0. Another one, electron B, transition from an excited state of 3 to ground state 2. Which electron transition releases more energy? Logically thinking, if you're going from 4 to 1, there's a larger leap of energy versus 3 to 2. So in fact, from 4 to 1 energy level, ground state, it releases more energy. And this would be electron A, example A. There's more energy. Why? Because there's more energy levels. Okay, so the electrons are jumping or moving, you can say, and that's the reason why. There's no calculation here. I didn't ask you one. You could have done both calculations and compared them, but I didn't ask you that. I asked you to theoretize. Sorry, the words are tongue twisted. And letter B says draw an energy level diagram. So if I'm asking you to draw a level energy diagram, this is where we draw the lines. So I'll have 4, 3, 2, and 1. Remember, N is energy level. This is my electron A. Electron B, I'm going to draw the same energy levels. 1, 2, 3, 4. From the last lesson, we found that our electron is depicted as like a half arrow because it's moving. So it is stated above that you're going 4 to 1, and the second one, B, electron B, is going 3 to 2. So I'm going to show this by an arrow going down, and then my electron there. My 3 to 2 is 3 to 2. That's a drawing. Again, remember that this is a big circular was showing all of the actual energy levels, but we draw them as lines so that way we can visualize better. It says also draw a rough depiction of the light waves emitted by transition B and A. So you're trying to figure out, comparing them, which one is giving off more energy. Well, we know A is giving off more energy because there's more energy levels going down versus B. So I'm going to make this wavelength of energy being emitted. So I'm going to show an arrow that it's emitted. I'm going to put the word energy or symbolize it by E versus, let's say this is smaller. The idea is that you don't know exactly what this is. This could be color. This could be an actual portion of the electromagnetic spectrum that isn't visible light, but you don't know that. You're just theorizing what it is. But I also ask you, tell me what you think the color would be if you're comparing the two. Well, here you have more energy for A versus B. More energy means you're down here on the visible light spectrum of violet or indigo versus red or orange. So I'll write red, or you could have write orange. If that's the case, you're going to compare this to violet or indigo. You could have just wrote red and violet or orange and indigo. What would be wrong is if you changed these colors and put that the more energy would have been red, because we know that that's incorrect. On the spectrum, we're looking at 350 is on the increasing energy versus the red, which is decreasing energy. Again, we don't know specifics, and I didn't ask for that in this question. This is just a theory. We're just comparing it. So you'll notice that same exact information is given, so you don't have to keep flip-flopping. But now, look at the information that I've given you. I've given you wave of 650. So you're observing that there's orange light. So you're somewhere here. If you look at my cursor, you're somewhere there. And it is 600 to 700. It's about 650. This is a more realistic question. And now you're going to go through. I purposely gave these questions in order so that way one would consecutively help you with the next and so forth. So let's look at number 2. You know the information. It's an orange light. Ultimately, I want to know how much energy that orange light is being emitted. Like how much energy is it giving off value-wise? So now you're calculating it. In order to do so, though, we have a couple steps. We're going to convert the wavelength from nanometers to meters. So this is a conversion process. We're going to convert it and we're going to set it up using proportions. We're going to use proportions because that's what they do in math class. So I'm going to continue on with that same math theory or not math, the fact. And we're going to use proportions for the rest of the year when we do conversions. So you are given 650 nanometers. You are looking for what it is in meters, convert nanometers to meters. That's the first half of your proportion. you're going to set it equal to information that you know. You know from above, 1 meter is equal to 1 times 10 to the 9th nanometers. So you need to make sure that you have nanometers on top because you wrote nanometers on top on the left side of the proportion. On the bottom, I would write 1 meter because 1 meter is equal to nanometers. Again, it's crucial that your units match on either denominator or numerator. When you do the math, you're going to multiply, it's called cross multiply, and then divide. And when you get to the final answer, you should be getting a whole number, so 6.5 times 10 to the negative 7th meter, because that's what you're looking for here. You want to make sure that you have a whole number when you use scientific notation. So if your calculator gave you another answer, but gave you more decimal values, you need to move it over so it is giving you one whole number. That's just a conversion, what we've done so far. That's A. Let's go to portion B. So problem B says now calculate the frequency of this light. From the speed of light equation, so speed of light is equal to frequency times wavelength. We know the wavelength that was given to us. So we know wavelength, we know speed of light, we're looking for frequency. So we can set it equal to frequency. And then we know speed of light, and I said we can use 3.0 times 10 to the 8th. I am going to write the units in all my work for this lesson so you see where the units come from for the final answer. Each unit is worth 0.25 on the exam, so I want to keep that in mind that you will automatically lose points if they're not units in the final answer. Let's see, I'm going to place my value that I just calculated in meters. So now you'll notice I can cancel out meters, and my unit is actually 1 over s, 1 over seconds. Now I'm going to show you how to use your scientific notation on the calculator slowly. So some of you, no problem, you know it. I'm doing this for everyone. So if you have your Texas Instrument, what you're going to do is type in 3.0. Do not type in times 10. Because this is a exponential, you're going to actually look for, if you have a TI, you're going to look for that EE button. It's usually above the comma. If you have a Casio, it's going to say EXP, exponential. So you're not going to have to do second function. There's usually a button that says EXP. Yes, there should be EXP. Thank you. It's on the bottom. I was told right now it was on the bottom of a Casio. For the TI, you're going to press second function and comma, and it's going to look like this. You're going to have 3.0 E. At this point, do not type the times 10, because what you're telling the calculator is you want to do it twice. So you're going to have that E. It might come up as an EE if you're using a Casio. So then after this, you need to give me what the exponential number is. In this case, it's 8, like that. So my first part, this top portion, I'm going to put my cursor and kind of wrap it around there. That top portion right there, 3.0 times 10 to the 8th, should look something like this on your calculator. Then I'm going to divide, and I'm going to put 6.5. I'm going to put second function, comma, on the TI it's comma, so it looks like this so far. And then I'm going to put -7. So my entire equations should look like this on the calculator. Again, if you type in times 10 anywhere here, it'll come out incorrectly. So you want to make sure that you have something that visually looks like this. Then you can press an enter, and out pops a long number. And I want to go over that answer right now. And I know I'm doing this slowly, just making sure that you can later, you can come back to this and pause as much as you want. So this answer is showing you a lot of decimal values, but you'll notice that there's the letter E. That letter E in computer talk is times 10. So this answer, 4.6, let's say round it to 6.2, is 4.62 times 10 to the positive 14. What that means is that it's 14 decimal points to the right. If you simply didn't put that times 10 or the times 10 to the 14th and only wrote in 4.62, that's a very small number compared to a very large number that it should have been. So it's very critical that you add that times 10. I also want you to get in the habit of not giving me computer talk, but actually placing times 10 in lieu of the E. So the answer then would be 4.62 times 10 to the 14th 1 over S. I'm going to box my answer in, and I'm going to get in the habit of boxing my answer in always. Okay, so that way there's no confusion. Let me pause. All right, so back to recording. Let's go to part C. I boxed everything in, so it's very clear. Part C is asking me to calculate energy. So finally, I can calculate energy. And let's take a look at which two. I've got two types of equations that I can calculate energy. Either E is equal to Planck's constant times my frequency, or I was given the highest energy level to lowest energy level. Nowhere here did I talk about energy levels. I've only given you frequency or wavelength. You've calculated for the wavelength. I'm sorry, you calculated for the frequency, my mistake. You were given wavelength. So in this information, we can use this equation of Planck's constant times frequency. Planck's constant is a given value, 6.63 times 10 to the negative 34 joules times second. You're going to multiply by the value you just solved for. Again, you can either use 2 decimal values or 3. And since I've already written 2, I'm just going to stick to the 2. 14 over 1 over S. So it should look like this. Let me figure out what my unit's going to be first. It's going to be S is canceled, S is canceled. If I cancel S on both sides, I'm left with joule. Joule is the unit of measurement for energy. One of, we have many. So if I calculate this by the way I've calculated the previous problem in my scientific notation, I should get 10 to the negative 19. Again, this negative is saying decimal point to the left, super duper small number, but with the energy level or the energy unit of joule. We will be using energy units of kilojoules, let's say calories for food calories that you see on packages, or chemical calories. There's a difference between the two. There are lots of different units for energy. In this case, we're using joule. All right, so that's a problem that's an example of a problem if we're given wavelength. So we ultimately need to figure out frequency, as you see, so we can use Planck's constant times our frequency. Well, let's say we aren't given that information. We are not given frequency or wavelength. Instead, we're given the information of, we're going to go from energy level 3 to energy level 1. There we go. I want to stop really briefly right here and notice how Mrs. Sulkson wrote out, how I wrote out, there's a bigger gap between 1 and 2. And I didn't do that by mistake. I did that on purpose. There is typically a bigger energy level jump between energy level 1 and 2. As you go further outward, the energy levels come together smaller and smaller. So your 4 is actually even closer and your 5 is there. Your 5th energy level is really trying to hold on to that center, which is the proton. And that's why it tends to pull inward. While your energy levels between 1 and 2 are the furthest away from each other because of the electrons repelling. Okay, so I did that on purpose because it actually does look like that. All right, so let's go to the problem now. Little side note conversations here of importance. All right, so this question says, what is the energy in joule or in joules released by 1 photon if the energy level goes from 3 to 1? So there's two choices of calculating energy. The first one we just did in the second problem, which was energy is equal to Planck's constant, which is the h, times the frequency, or we have the second one that's also equal to energy. We use the RH constant, and we have the highest energy to lowest. Well, this is giving you a high to a low, a 3 to 1. It's releasing energy. What type of energy? Let's find out. So I'm going to write out the equation. E is equal to negative. Do not forget that part of the equation. Then I'm going to write in the actual RH constant, which never changes. 2.18 times 10 to the negative 18 joule. The rest of the equation has brackets around there. It is 1 over the high squared. Well, the highest energy level was 3, and it's squared. The lowest energy level is 1, and it's squared. So for this example, I want to go over every single mathematical step. So if you're struggling at all, you can always pause and go back to it. I'm going to bracket it. I'm going to rewrite this portion because it doesn't change just yet because there's no calculations involved. Now I have 1 over 3 squared. 3 squared is 9. Minus 1 over 1 squared. 1 squared is 1. If I do the common denominator, and I have negative 8/9, I'm going to rewrite that equation over here. Now it's time, 18. Energy, energy. So now you're going to multiply. 2 negatives is going to give you a positive answer, and you're going to solve for energy. You should get 1.94, or you can use 3 decimal values times 10 to the negative 18 joule. Box it in so it's very clear that you know that that's the answer. So I've shown a lot of work there. I'm going to scroll this up just slightly. You'll still see it. So again, this is how much energy is being offered. So as it's going down from 3 to energy level 1, it's emitting something called a photon of energy. We don't know. We know this is the amount of energy in joules, but we still can't determine, let me see my cursor, we still can't determine what kind of energy. Ultimately, if you look further down, letter D is going to identify which type of energy it is. Is it visible light? Is it not visible light? We need to determine it from a little bit more calculations. So let's go to letter B. All right, letter B says, what is the frequency of the light released? So we don't know the wavelength in this. We only know the frequency. We don't know the wavelength, we just know the frequency. So we're going to try to figure out what we've given. We're given energy, I'm sorry. We know Planck's constant, and we're trying to solve the frequency. So we don't have any other information. I think I misspoke and I said we had wavelength. We don't. I'm sorry if I misspoke that. But we do know we solve for, let me just mark that up. I'll use this yellow. This information is here. Okay. I'll mark this up. H is our Planck's constant, which is right up here. So with the knowledge of those two values, let me go back to my inking. I can now solve it. 1.94 times 10 to the negative 18th joule. If I'm trying to isolate out, E divided by Planck's constant will give me my frequency. So I'm going to then divide my Planck's constant. Planck's constant is 6.626 times 10 to the negative 34. 6.626 times 10 to the negative 34. And the unit is joules times seconds. I always try to put the unit there to remind you what the end result unit will be. I'm going to cancel out units, and I'm left with a unit of 1 over S. I'll type this into the calculator. Remember, like a gentle reminder here, this times 10 in the calculator is exponential only. you don't type in times 10 anywhere. You can go back just a few minutes from my lesson to review that again. But keep practicing that scientific notation on the calculator. So, oh, this is kind of scratchy there. The frequency would then be 2.93 times 10 to the 15th. I'm going to box it in for my answer there. I still have two parts before I can help figure out and determine what my type of energy is. So here's part C. Let's put this down further. It says in C, it says, what is the wavelength of the light released? And I want you to calculate it from meters, so convert it from meters to nanometers. The reason you want to do that conversion is because if you notice on this electromagnetic spectrum, the units being used are in nanometers. So if you don't convert them, you won't be able to properly answer that last part of the question. So we have a lot of information so far. We are looking for the wavelength. In the equation above, we can actually solve for the wavelength, which is that right there, that symbol. If we rearrange it, speed of light over frequency equals wavelength. I'll round my speed of light since I believe that's what my students had said they were used to from last year. And then my calculation from my frequency from the previous problem, and 1 over S. Let's take a look at that unit really quick. S is going to cancel out, and I'm left with meters, which is the answer should be. I'm not done yet, I'm gonna have to convert it, but let's do the math. 3.0 times 10 to the 8th. Remember that times 10 is that E or that exponential key. So EE or exponential key. Do not write in or do not type in times 10 and divide by that. And I ended up getting 1.02 times 10 to the negative 7th. I'll box that final answer in so it's really clear, and then I got to convert. I'm going to do my conversion over here on the left side. I know I've been given 1.02, not given, I calculated, excuse me, and I'm trying to find out how many nanometers. So the left side of the proportion should look like this. It's then equal to my actual conversion that I know, and I know 1 meter is equal to 1 times 10 to the 9th nanometers. So 1 meter is equal to 1 times 10 to the 9th nanometers. Remember, when you're setting up a proportion, your units need to be the same on both the numerator and the denominator. Because there's an equal sign, it's cross multiply, in this case, the two numbers that are cross multiplied, and then divide by the other. Since it's dividing by 1, you just have to cross multiply. You cross multiply and you get 102 nanometers. So this leaves us to D. D is ultimately asking what type of light is released. When I say type of light, that's energy, not necessarily visible. So let's take a look at the visible light. From previous, just a few minutes ago or a little while ago, we realized visible light goes down to about 350 and it goes all the way up to about 800. Your ultraviolet starts at 10 nanometers and goes up to about 350, 345. So at that point, our 102 falls right about there. It's not quite visible light. It's not actually close to visible light. So we have an energy of something called UV, ultraviolet. It is not a color, in fact, and it's not visible. Okay. All right, so I'm going to stop recording at this time, and I will post this recording. I'll go through any, or recording rather, I'll go through any questions that we have.